Okay. So if you do it and later on and you only get your A and your B, that's because your diagnostic is turned off. Some people last semester, for some reason, they swear they didn't take out those calculators and it still set it to off for some reason. So if you do this program and you only get your A and your B and you don't have your R's, you just need to turn your diagnostic back on, which you just go to second catalog and turn it on. If you can't remember how to do that, you can look back in your notes. If you're in the middle of a test and you don't have an R and an R squared, let me know and I can get it back for you. But our R for this one is going to be 0.901. Right, that last number that we see. So this is R 0.901. I think they usually have you round it to 3 decimal places. So 1, it's positive, which is right because our scatter plot was pointing up and to the right. And 2, it's actually pretty close to 1. This is a really good R, which makes sense because when we did our scatter plot, these points were a lot more like linear than the other example. So you can come over here and compare the 2. Right, okay. So here's the 2 examples that we did. This one we had an R of 0.773. This one's positive. You know, it's a decent linear relationship. But if we look over here, this one's 0.901. This one is 1 positive, but it's also a lot closer to actually being linear. You have this one that's a little off and this one that's a little off, but other than that, it's pretty much in a straight line. So this one's very close to being linear. This is a much stronger positive linear relationship than this one is. You can tell that, 1, by looking at their scatter plots, and 2, by comparing their R's. Since this one has a larger R, there's going to be more evidence that these 2 are going to be, that they have a correlation than there is evidence for this one. Okay. That's all you have to do to find your R. So like I said, a lot faster than trying to do all this stuff. Okay. So we talked about comparing our 2 R's. This one was a stronger relationship than the other one. This one was 0.9 and the other one is 0.77. But at what point do we say it's not going to be linear anymore? We're going to have to compare the correlation coefficient to a critical value. So for this one, the first thing we're going to do is figure out the absolute value of the correlation coefficient. And that's just because I think we do an example of this later where we have a negative R. All right, and that's just because it's okay if it's over here, it's okay if it's over here, we just don't want anything here close to 0. So we're just going to look at the absolute value. So if it's negative, just look at the positive side of it, just drop the negative when you're doing this part right here to compare it. You're going to find the critical value in table 2 for the given sample size. This one, when you go through to do your homework, when they want you to do these types of problems, there's a blue link you can click on, table of critical values, and it'll bring up this table for you. So you don't have to you know, print it out or keep your notes with you when you want to do these types of problems. You can access it just on your computer, and it'll be linked to the homework problems that they want you to use that for. So we're comparing the absolute value of the correlation coefficient to the critical values. The critical value is kind of like the cutoff point. If your correlation coefficient is greater, so it's closer to 1, then we're going to say that there's a linear relationship. If it's smaller than your correlation coefficient, then we're going to say that no linear relationship exists. So let's do an example for this. So we did the drilling depth. We found that that R was 0.773. We didn't really find it. They gave it to us. But this is the R for that one, 0.773. And now we need to find the critical value. The critical value is going to depend on how many data values you have in your sample. So if we look back up for our drilling data, first one we had, right? Nope, not that one. Here we go. Our drilling data, how many points did we have? I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 12 ordered pairs, 12 points on my scatter plot. So I come down here, my my n for that data is 12. So if my n is 12, my critical value is 0.576. Alright, so that's my cutoff point. It's 0.576. Anything greater than that is considered linear. Anything less than that would be not linear. So in this case, since my absolute value of r, which is 0.773, is greater than my critical value, which they said is 0.576, then we say it is linear. So if we did a different example with n equals 12 and we got an r of 0.42, that would be too small. So it's going to be a little too close to 0 for our liking. We'll say that it's not going to be linear. So this next example is just correlation and causation. We talked about this already in chapter 1, but like I said, all of the ones that we're going to have in this chapter are going to be observational studies, so we can't say that a correlation necessarily implies that there's a causation. So for this example, they say the percentage of female population with a bachelor's degree and the percentage of births to unwed mothers since 1990 is 0.94. That's a pretty big R of 0.94. It's really close to 1, so those are going to be really strongly correlated. And so they ask, does this mean that a higher percentage of females with a bachelor's degree causes a higher percentage of births to unmarried mothers? So if we take a bunch of people without degrees, or women, and put them through the program, give them a bachelor's degree, does that mean that there's going to increase the number of births to unwed mothers? So the answer to that one is going to be no. So this one is no. Both variables have increased over time. So that's going to be the case with some of these things. You see something that does increase over time. Two different things that both just happen to, time is something that has an effect on both of them. So things that are completely unrelated, some people have a tendency to say they are related, but it's just both of them happen to be increasing as time passes, because now it's more common for women to get a bachelor's degree, and it's much more socially acceptable for unwed mothers to have a baby. So the other thing that could, instead of them both just increasing with time or decreasing with time, or one increases or decreases with time, is something called a lurking variable.